Hello and welcome. Thank you so much for joining us. Today I have Steve Baumann on with me. Hello, Steve.
Hello, how are you guys?
I was on Twitter and a young earther responded to a comment that I made that one cannot hold to young earth and be an informed person. One is either willfully ignorant or deceptive. And he asked, "Can you respond to this point by point?" And I said, "Yes, I can." And he said, and so that is why we are here today, because the video that he sent me was flood geology. And some of you know that my understanding of geology is pretty doggone weak. So for me to take that kind of confidence on a video on geology, which I know very little about, tells you that I don't give much credence to the young earthers. And thus Steve is here. Hello, Steve.
Hey, just in case anyone's interested too, when you do it, the avatar that I picked, that's the Gardar ruins in southwest Greenland. It's a chapel, actually. There was a bishop that stayed there in the 16th century.
That's cool.
It's now called Igaliku. There actually is a town right behind it. They are presently excavating this thing. Bishop's buried there.
All this evidence for the flood hasn't been disproved. No way it has been disproved. It was just assumed wrong and was rejected for unscientific reasons. A lot of us are bringing back the flood into Earth history. And you know something? We are finding solutions to many mysteries out there in the rocks.
This is something I hear over and over. That young Earth creationists make the claim that it was just assumed to be false. That is absolutely incorrect. You look at the literature, and I've dug into the history of geology before, even wrote a short book about it. But you go back to the 18th and 19th centuries, and initially all they had was the Bible. They didn't know what they were doing. They didn't know where they were going, and it was Western civilization. It would have been some other, if this revolution happened in the Middle East, it would have been the Quran. It's whatever they had, and that's all they had. And when they actually went out looking, instead of finding evidence for flood, they found evidence of ice. And everybody likes to think of Darwin as the founder of evolution, and he was, but he was also pretty good at glacial geology. It was kind of like his thing on the side. So that's how it happened. And when they found that, they started looking into it. They started developing techniques and principles. I mean, Steno's laws have been around for a long time, but they were trying to verify those. And as time went on, we realized the Bible is not a book of science. It can't be used. It was not assumed to be false. It wasn't just thrown to the curve. That never, ever happened. And I really wish they'd stop saying that.
We are finding solutions to many mysteries out there in the rocks, of which this series shows you mysteries from the field of geomorphology.
Okay, geomorphology is the study of landforms. Like, I don't know if you've ever heard terms like yardang. That's a geomorphic feature. It's not a geologic one. Because geologic structures and all that have we use different names. It kind of falls under geography more than it does geology. Hills, anything that forms a hill. Hills are geomorphology. Any land shape is geomorphology, and they have names like yardang and all that for that stuff. And some common ones like hill, mountain, valley, the ones we all know. But the geology affects the landforms. The geomorphology is controlled by the geology, tectonics, and erosion. Those are the primary, and geomorphic features are not permanent. They change. That mountain that's here today isn't going to be there 10 million years from now. It won't look the same. They're dynamic things. So you can't really go by Earth's history of studying the shapes of things on the surface. That isn't really something you can do. You can use things on the surface to clue you in, but you still have to go up there and you still have to go and see what you're looking at. Like terraces on the side of the hill and a river in the valley might clue you in that the river was higher at one point. But you got to go there and go and look at it. You can't just say, in my mind, the shape, that's the only way it can form. You can't do that. Geomorphology is like the watered down Diet Coke of geology. It's very few people it's usually kind of like a side thing. You're either a geographer or you're a geologist. It's not really something people do as a career because you can't really do it as a career.
The guy that's doing the presenting, he is a meteorologist.
Okay, I was going to ask you what's his background. Do you know his education level or no?
He has a master's in meteorology.
These are mysteries to uniformitarian evolutionary geology because they can't explain them by slow processes over millions of years.
There's so much wrong in that little statement right there. I've talked about this before. Uniformitarianism is not a scientific theory in the modern sense. It is a school of thought. There were many other schools of thought in the 19th century, like Plutonism or Neptunism. There were actually people in the 19th century that thought rocks literally precipitated out of the water. Now we know evaporites can and limestones can, carbonates, but they thought things like granites and sandstone did too. So it was just kind of a school of thought, but you never hear young Earth creationists talking about that. I noticed he said millions of years. I hear that in every young Earth creationist video. That couldn't happen in the millions of years. We know not every process takes millions of years. Glaciers that moved and covered the continent, mostly in the Quaternary, and a large part of Europe and Eurasia, those are on the scale of hundreds to thousands of years. These are not millions of years, everything. We know this. And there's some processes that take a lot longer than a few million years, like the assemblage and breakup of supercontinents.
They might be a mountain range, it might be a valley, it might be a planation surface, it might be a pediment, it might be a submarine canyon. You include the bottom of the ocean in geomorphology, by the way, the surface shape of the bottom of the ocean. Many landforms that are common all over the Earth cannot be explained by slow processes of erosion over millions of years. For instance, one of the most significant landforms all over the Earth are planation surfaces. Some of these planation surfaces are very large, like most of Africa is either one or a couple planation surfaces that cover 60% of the continent. That's why it's so flat on Africa. Like the Serengeti is flat. You see animals moving on it on a flat plain. That's the Serengeti. But look at the sedimentary rocks and metamorphic rocks below there. They go up like this, which means before they were plain flat, they used to go up like this, and then something just sheared them off.
Planation surfaces, or planes, as most people know them. And he did that planar thing that I see young Earth creationists do, as if something was scraped off the surface of the Earth. Like they did that in their Baraboo video, yet I can take you to this another place in Baraboo. That's their great unconformity that they're usually talking about. But he can't be talking about that here because he's talking about geomorphology. And that's only things that exist now. You know, I mean, you can look in the rock record and you might see paleotopography in it, but that's harder to see because it's in the Earth. These plains, these formations of plains happen many different ways.
He said something sheared it off.
Yeah. Okay. What he's talking about is, and I'm sure he'll come to the Grand Canyon because they always frickin' do. That's their go-to place. What he's talking about is an angular unconformity. There are plenty of angular unconformities in the geologic record. It's not just between the Precambrian or the Cambrian. We have a great unconformity forming right now if you live anywhere in the continent. It's forming now. All that means is that there was enough erosion to happen at some point, and then more sediments came in, either through basin formation. You know, it's tectonics is the driving force for all of this. It really is. What he's talking, they like to talk about that shearing thing. And like I said, they usually do it for the great unconformity, like to say it's flat and level, but I can take you to many places, the great unconformity, put my fingertip on it, and it's vertical, like at Baraboo, Wisconsin. I mean, that was a sea cliff that stood as the Cambrian seas transgressed. They never talk about these things. Even they take you to the Grand Canyon, they're like, yeah, this sheared off. But there's places that they don't take you to where there's things like paleotopography, you know, little hills, little knobs that stuck up as those seas transgress. They never show you these things.
Is a plain area a sign that there is less tectonic movement underneath?
Generally, it's a good question. Generally, areas where there are plains are stable. They're what we call the craton.
Okay.
That just means now. But you can get hills and mountains in the craton areas. All you got to go do is go to the Lake Superior area, you know. But generally, yes, it's stable. Now there are exceptions to this, and you can get uplifts of an entire like plateau, like the Colorado Plateau, which is huge, which their precious Grand Canyon is on. which is uplifting, but it's not forming a mountain. The whole plateau is kind of uplifting. And that has to do with several factors. It has to do with the North American continent burying slowly the East Pacific rise. It has to do with Yellowstone. It has to do with basin and range extension. It's all tectonics.
We don't observe planation surfaces forming today, except on a very small scale when a river floods the edge of the river and cuts maybe some tilted rocks, possibly, erodes that flat. Otherwise, the scale of these is so huge, you don't see them forming over large scales. But if we wanted to use the river as an analogy, look at the scale of the one in Africa. We would need a river the size of Africa. Well, what does this mean? Well, we're talking about the Genesis flood and the sheet erosion planing the land. As Africa was coming up, the waters were running off.
If he was right, shouldn't the entire world be a plain?
Everything would have been cut down to probably about sea level.
Okay.
Or close to it. And that's not what we see. And he's obviously talking about the modern land surface, which, young Earth creationists, if he thinks that the modern topography is because that's where the flood sheared off, and all other young Earth creationists are talking about the great unconformity, they're talking about two totally different things. And this might be confusing to someone who doesn't know what these things are. So it seems to be like he's talking about the modern landscape, which isn't, there's nothing sheared there. If there was things sheared, we wouldn't have mountains.
Could even a river that's moving extremely fast actually shear rock like that?
Rivers with high velocities can move big things, but his river analogy, which is more like a direct equivalence, they say analogy a lot when they mean direct equivalence. It's the same thing. Rivers only can have so much power behind them. It's not just a function of water speed. It's a function of the volume of water that's being pushed downstream. And yes, rivers can move things like boulders, but when they get down in a low area, what that's called the old age phase, it has to do with relative erosion. It doesn't have to do with actual age of the river. You get the meandering and river velocity plummets, and you're not going to move that. The Nile isn't moving big, huge boulders. Okay. And there's no uplift in the area. So it's not cutting down still. What happens when a river reaches its baseline, which is what happens, starts cutting laterally. It stops eroding down because it can't erode less than sea level. So, because it would become a part of the ocean then, it would flood in.
He says that, a river can shear something. Okay. But then he's saying that because this was across the entire continent of Africa, that would mean you would need a river so wide it would cover most of the continent. And so he's saying this would be a global flood. But a flood doesn't move the same way a river does. And especially a flood that's 20 feet deep, I would think it would have far less impact on the rocks at the bottom of it, wouldn't it?
Well, that depends. And you're absolutely right. Flood is a totally different thing. The mechanics are totally different. The closest thing we have analogous to that is probably what we call sheet outwashes. Happens at the end of glaciers and stuff. And when you get that, as a matter of fact, Lake Missoula in Montana did this. When that ice dam breaks or that end moraine breaks, you get this catastrophic outwash. But like any flowing water, it's going to lose energy as soon as it hits some sort of level area. You can't just keep pushing this thing. Could floodwaters that are a mile deep move big, huge boulders? Yeah, because the volume's there, but the speed isn't there. You can't move that kind of mass of water without generating heat. Friction and physics is all a part of this. So in order to do that, you got to raise the temperature to get it to move faster, or temperature will raise as it moves faster.
You mentioned the heat, and I don't know if you're familiar with Erica Gutzik-Gibbons' videos on the heat problem, because the whole flood Earth model has a huge heat problem, and geology is only a small part of it. The greatest part of the heat problem comes from trying to compact the radioactive decay of millions of years into 1 year for the flood. And she had someone go through the math and figure out how many times the Earth would have been vaporized just from the heat generated from that. But if you're saying that the heat generated from a massive flood causing the shearing of this rock would also be an issue, that would just add one more level to the heat problem that they already have.
The heat problem actually has several components to it.
Right.
It's like you said, it has to do with radioactive decay. It has to do with friction, moving waters, and they even think continents slid about, creating even more friction. And then the ones, I don't know if you remember Hovind, back in the day, he had this concept of an ice like sphere floating above Earth.
Some people have argued, oh, no, you can't have an ice meteor and come through the Earth because the Earth has an atmosphere and it'll melt it. I understand all that, okay? If the pre-flood world had a canopy of water above the atmosphere and squeezed it down to maybe 20 miles of atmosphere, it would double the air pressure. Plus, an ice meteor now, if fragments are coming through, sure, a lot of them get vaporized, not only from the temperature, but from the friction, you know, just building up friction. But just like you can spray a hose right through the middle of a fire, I think you could do the same thing with a stream of ice coming in toward the poles. You would get, it would develop a cold channel where a certain percentage of it would survive the journey.
They've kind of abandoned that because people have run the math on this, and it's not difficult math. As a matter of fact, a guy called Thunderfoot did it recently in a video to get that ice to come down. Now, we think of, he did it in respects to cooling the Earth off by throwing a comet at it, which wouldn't work. You think that, oh, ice cold must, you know, fall. And well, anyone who's ever seen a spaceship under the atmosphere knows there's heat, there's friction generated. And depending on the velocity of that incoming object, even if it's slow, it's going to generate heat in the atmosphere. And if you've got a sphere of ice crashing into the Earth that's up there at I don't know how many kilometers or whatever the hell they think it is, or did, you're going to generate heat. So you've got the heat of the falling ice, if you accept that. You got the heat of the sloshing water. You got the heat of the continents moving. You got radioactive decay. The planet would not be here. You can't use the laws of physics as they are. You have to either go, the miracle happened here, which is completely unscientific because science describes the natural world, not the supernatural.
I don't know why they don't just say that God put Noah's Ark into a bubble, lifted it off the earth, replaced the planet, and then put the bubble back down on the earth.
That's just as realistic as any other thing they come up with.
It's the same with the other continents, but there was a lot more tectonics on other continents, so you broke up these planation surfaces that were once much larger by tectonics and erosion. So now you just have erosional remnants of planation surfaces. They're smaller. Like the high plains is a series of 4 planation surfaces caused by erosion. You had one level up here that covered the high plains of Canada, Alberta, and Montana, parts of North Dakota and Wyoming. It spread the resistant quartzites on these, and then most of it got eroded to where you have small remnants here and there. Like the Cypress Hills.
I have no idea what he's talking about.
He doesn't either.
Oh, okay.
What I'm seeing here is an intentional leaving out of something you taught about in high school earth science, and that is the glaciers. He just mentioned a couple provinces in Montana, they were all glaciated. Glaciers moved these things. We know this. Rivers cannot move as large of objects as glaciers can.
Okay.
Glaciers don't act like bulldozers. That's not what they do. They erode by plucking and abrading. They've got that mass behind them, even though they move slowly than a river. So they can pick up huge things. There's a boulder in southern Illinois that's 10 tons of white quartzite. It could have only have come from the Lorraine Formation in Ontario, which is Precambrian. I study that. So having quartzite hundreds of miles away, yeah, the glaciers do that. And then if
Couldn't have happened in a global flood?
No, and I mean, we could see end moraines, ground moraine, outwash channels. Matter of fact, I already mentioned Lake Missoula in Montana was a catastrophic outflowing of a glacial lake that was huge. So he's not even talking about that. He's just talking about, oh, the ground is flat, therefore flood. You can't argue your way into evidence.
Were there fewer glaciers in the African continent?
There were none.
There were none.
There were none.
Okay. Okay. That explains the topography better.
Yeah, the southern hemisphere, other than Antarctica, it was pretty much ice-free. There was nothing. It's pretty much a northern hemisphere thing. And the glaciers reached the furthest south, actually in Illinois, about 31 degrees north. Now, there wasn't one sheet that just moved down to that latitude. In some places it was at 45 degrees latitude, and and we had several advances and retreats. So you had plenty of time to level things. And there's places that were glaciated that aren't level. He's not mentioned the glaciers, which is annoying me.
Cat by 75 feet of rounded cobbles that come from 400 miles away. And also, speaking of those cobbles, that's another big mystery in uniformitarian geology, because they've been transported way too far for normal rivers.
Looks like outwash deposits to me. So what happens is the glaciers carried all that stuff and it was in the ice. The ice melted, formed ground moraine and moraine. Then there was probably a little glacial lake or something behind it. And you see this a lot. You get catastrophic outwash deposits. You see the Kankakee River follows in Illinois. It was Kankakee Turret. And in there, it's going to deposit quickly cobbles and boulders of stuff the glacier was carrying. And if the glacier's already moved over something 400 miles away, it's going to be a mix of that rock and the native stuff, the surrounding stuff. So there's no problem in geology here.
Plains of Montana and Alberta and Saskatchewan and even Manitoba and even North Dakota, from the direction of the currents we can determine from the rocks and also the sand inner beds. It came from the southwest, which the closest location of quartzite in the southwest is in central Idaho, and that's across the Continental Divide. So if we had normal rivers depositing this, they'd have to come over the divide and get spread way out there. In fact, the furthest spread of these quartzites is 800 miles. And this is not an unusual pattern for the Northwest states and adjacent Canada. You see this pattern around other mountain ranges of the world. These are mysteries of how could this happen under millions of years of time. Also, pediments aren't being formed today. Submarine canyons aren't being formed. They're being modified.
There's so much wrong there. I could tell he stumbled a little bit, trying to figure, because he doesn't know what he's talking about. Somebody gave this guy a script, obviously. Like, I feel sorry for him. But yeah, I mean, it's glacial geology, and you can get current direction from the deposits. You measure the direction, you get cross bedding, and you measure the planes on the cross bed, and I'll tell you the direction the stuff came from. That works always. We know that. But to actually know where that quartzite came from, because he said it came from the southwest, which doesn't make sense. There's a lot of quartzite out there, a lot. You can't just say, oh, that's quartzite, and there's quartzite in Arizona, thus that's that quartzite. You got to take your butt up to the quartzite, hammer those rocks open, and see if they match anything anywhere else based off the flow direction. Any sort of bedding that indicates flowing from the southwest or south. I don't know where he got that from. I don't know if he's looking at rivers into, the Great Salt Lake or what, but that is a nothing. That's just a completely false statement.
They're being deepened a little bit or filled a little bit, but that's all we observe. Water gaps and wind gaps aren't forming today, except on a teeny.
That picture he just showed was a U valley carved out by a glacier. I don't even need to know anything about that picture. I can tell just by looking at the geomorphology that, because glaciers form U valleys, rivers tend to form V valleys through the mountains.
Very small scale, but some of these water gaps are really deep. There can be a mile deep or 2 miles. Some coming through the Himalaya mountains up to 4 miles deep. In the Zagros Mountains are up to 8,000 feet deep. So these things are huge gorges cut through mountains. These are not forming today, and so they're huge mysteries trying to account for them. How does
I get why he's saying these are not forming today, but isn't the evidence against that just extremely overwhelming? I mean, we know the rate at which the Grand Canyon is getting bigger every year.
Yeah, we do. And these things are forming somewhere else. They're just in the beginning stages. Why? Because the processes are slow. These are not quick processes. They think, young Earth creationists think on the scale of a human life. They can't get past that. Otherwise, they wouldn't think the Earth is 6,000 years old. You know, you hear them talk about radiocarbon dating. It's like the rocks I mess with, radiocarbon dating isn't even a thing because they're billions of years old. I can't even use that. As a matter of fact, there were no macro life back then. But, you know, yeah, these things are still forming. And they're still being carved out. And like you said, we can measure erosion rates. That's not magic. I mean, he keeps saying mystery of this and mystery of that. But all you got to do is study the stream patterns, rates of erosion, and the deposits. That's all you have to do.
How does a river go uphill and cut that water gap? Well, they have a lot of ideas. There's usually evidence against these ideas out in the field. Well, the evidence shows that the flood can readily explain these features of geomorphology.
Rivers had to flow up hills. They can't explain that. Yeah, because we don't say that. No one says that except you, dude. Oh, that's not a thing. No geologist ever said that. It's not necessary part of the process. It's just his script writers making stuff up for him.
Now, generally, rivers flow from north to south in the northern hemisphere, correct?
Yeah, it depends unless you're on the South Shore of Lake Superior. But generally, yes, generally.
Okay. And if the force of that river is such that, you know, it goes uphill, would it not still go uphill?
The river, well, we'll assume it's dammed downstream or something. A river can go uphill if a dam is formed and a lake flows. But as long as there is a gradient, a river's not going to go uphill. It just physically can't. That's not how physics works. You need to dam it up, and then it's just going to flood up slowly. But rivers don't flow up hills. That's not a thing.
Yeah. But if a river is running into a hill, wouldn't it erode the hill then, possibly?
Or move or go around it.
Okay, or go around it. Okay.
Yeah, they're lazy like people. Yeah.
Some people think, well, hasn't the flood been disproved? Even though we have all this evidence for the flood, hasn't it been disproved? No way it has been disproved. It was just assumed wrong and was rejected for unscientific reasons.
No, brother.
It started back in the Enlightenment.
All right.
Enlightenment started in the 1700s when intellectuals and scholars and educated laymen, they thought they can explain everything without the Bible. So they rejected the Bible, especially Genesis, creation and the flood, the Tower of Babel incident for the origin of the languages.
I find it odd that he's saying that, you know, they read a bunch of laymen. Well, he's a layman here rejecting geology.
I was going to bring that up, but you did first. And we've already touched on this, but I mean, he's talking, this is just talk. He says evidence and he just makes statements and shows a bunch of pictures. That's not evidence. The history geology book I wrote on the history of geology is full of references. We know young Earth creationists don't use evidence, so let's go.
And therefore they had to explain all of Earth science by processes going on today, present processes or uniform processes they called it. That's why the idea became called uniformitarianism. Uniformitarianism was developed by James Hutton. And also Charles Lyell embellished on it and actually made it more popular, starting in 1830 and finishing in 1833 in 3 volumes of the Principles of Geology.
That's actually true.
Was this a conclusion of science
I have
at the
those
time?
books.
They had a lot of crazy ideas of geology at the time, thinking the sedimentary rocks were the results of heat action. They knew hardly anything about geology, but they arbitrarily rejected Scripture, the flood, which has a lot to say about geology. Bible's a history
has nothing
book.
to say.
The Bible has a lot to say about geology.
I'm pretty sure the word geology is nowhere in there, nor is anything alluding to geology.
I think he says that because it uses the word mountains.
Yeah, mountains are not.
And rocks.
He doesn't know. He's just saying
what happened in the past. And by the way, no scientist was there to observe this. So it's
Not
based
that
on
bullshit
interpretation.
again.
So the interpretation became the Enlightenment.
And you weren't there during the flood, dude.
An arbitrary assumption that continues to this day. And the rejection of the flood was not because of science, it was because of personal rejection arbitrary
No,
decisions,
that's what you guys
subjective
do.
decisions they made.
Yeah, because these guys weren't out to disprove the Bible.
A lot of us are bringing back the flood into Earth history.
You should just have one bullet. I'm full of shit.
Well, when we read Genesis, we divide biblical Earth history up into a number of time periods. There was the time of the creation, which on day 3, there may have been geological work when the dry land appeared from the waters. That's still uncertain because creation was one giant miracle. Then we had a pre-flood period for approximately 1,700 years.
I see already interjected the miracle.
Geological action. Then you had a Genesis flood for 371 days. And then
when I first watched this, I backtracked 3 times looking for the pre-fall period, because according to them, the Earth was very different pre-fall than it was post-fall. And yet that's not one of their periods. The pre-fall period is not even one of their periods.
Oh, that's interesting.
Then it comes to a peak approximately day 150. It appears that water rose fast for the first 40 days, and that's what you'd expect in the mechanism being so catastrophic. You'd expect most of the flooding soon, and then the Bible talks about it prevailing up to day 150, so that kind of implies a slow rise. And then the ark rounds on the mountains of Ararat, and that would indicate that's probably near the peak of the flood. And then day 150 to...
If the rain stopped on day 40 and the fountains of the deep don't open until here, where is all this additional water coming from?
They don't know. They drew a graph and said, look, we made a model, but they have no testable hypothesis behind their model. Henceforth, the whole thing's garbage. And that was a good point. I mean, I could draw a graph of how a stop sign grows out of the ground. It doesn't mean they do, because I have no evidence to back that. Oh.
But if God can pour fountains of water in through the dome, or whatever you're going to call the atmosphere, why did he even need the rain? The rain wasn't even necessary.
I don't know. Some of them say the fountains of the deep were erupted from below. I know Steve Austin's one of those guys. He's one of those guys, and we have hydrous minerals in the mantle, and they say there's water in the mantle. And I've even seen scientists write that as a title in a paper. But it's not true water. It's bound to the mineral. It's OH ions. So, I mean, if you relieve the pressure, it would bond and become steam and blow up. But I mean, then you've got the heat problem again. It's just,
well, and then the next question is, since the rain stopped here, but water kept coming into here, where did that water go? Back where it had been? Back down to the deep?
I have no idea.
Yeah, the water from the windows of heaven, that's going to have to go back up to heaven. What do they have? Some kind of massive evaporation.
Yeah, or these are solutions I've heard them use to try to get around that. Is that, well, it went back down in the mantle from the plates, which would just lubricate the hell out of the plates and cause massive magma chambers to form, because the mantle is a solid. People don't understand this, with little magma chambers in it. But when you add water or release pressure, you can lower the melting temperature of that rock, and it liquefies and becomes magma, rises to the surface. So if you're throwing tons of water in the mantle, you're going to get eruptions everywhere. And their book doesn't say that. Or another way around it that I've heard is that the water didn't really rise. It sloshed over the continents. The existing oceans moved over the continents, and which we're right back to the heat problem. And they all have different ideas. If any of this was backed by evidence, they would naturally come to some sort of consensus. But they can't. They don't, because they don't have anything.
Day 371, a total of 221 days, the flood is draining off the continents. As the continents rise up out of the floodwaters, and the mountains rise and the valleys sink down and the ocean basins sink. So we can divide up this flood into a flooding stage, which should be your first 150 days, where the water rises to a peak, and then a receding or retreating stage.
Retreating to where?
Those up into
phases. That's what I'm wondering too. I'm also wondering, would the retreating water, would the movement of the retreating water generate even more heat?
Yes, and that's something people don't realize, that when you move a lot of water really fast, you do generate some heat. Now, on this scale, you would generate a lot of heat. But even a landslide that's caused by oversaturation of soil generates a little bit of heat. You know, you're moving something, you're turning that potential into kinetic energy. It's not just not going anywhere.
First phase would be the first 40 days when you had huge catastrophism, huge big currents, a lot of turbulence, because the mechanism is so powerful. And they had 40 days and 40 nights of rain that probably was the cause. 40 days is probably telling us that it was waning, the mechanisms were slowing down.
Probably.
Yeah.
Water's covering the earth.
I have no model, but I have a graph.
Yeah.
That's all I was saying.
This is what I think.
Yeah.
Water's starting to recede. When it's doing that, the water's moving across the earth in wide currents and probably fairly deep, probably several miles.
Probably.
We call this the sheet flow phase, because the water currents, if you looked at them down current, they would be very wide, maybe 1,000 miles wide and 2 miles deep. We can bring that to smaller scale. They'd have the shape of a sheet, very thin and wide. So we call it sheet flow. But as more mountains are exposed,
I'm fine with that. I'm fine with that. I mean,
they rose up.
Yeah, he's describing sheet flow. Okay.
Plateaus were exposed also. The water's forced to channelize around these. Then we switch from more of a sheet flow to more of a narrow current, and we'll call this the channelized flow phase. Now, each of these two phases during the retreating stage of the flood erode the continents in a different style. Sheet flow generally will erode huge areas and cause planation surfaces and transport resistant rocks from that erosion process long distances.
I really wish they wouldn't show random pictures like that of not what they're not talking about. I hate that.
If the flood had really happened, would we not see evidence of these things he's talking about?
Yeah, we know what large scale flooding events, what kind of deposits they leave behind. We know what these things look like. And it doesn't look like this. And notice he's talking about the West, where you have the Rockies, the Laramide orogeny at the end of the Cretaceous, because all that was pretty much seaway until during the early tertiary period. And then you have the ancestral Rockies and the modern Rockies. I'm not going to get into that, but you had uplift of the whole continent and the sea drained. Well, that gives you kind of flat land there. And then you had the glaciers come in and do things millions of years later, during the, 2 million years ago during the Quaternary, which we're still in. Plains are the default of the landscape, I would say, if there's no tectonics. And even plains aren't perfectly level and flat. They're going to have little streams cut in them. You drive along the glacial parts of Illinois, in the middle of Illinois, that landscape is 26,000 years old. And yeah, generally it's flat looking, or about 20,000. It's flat looking, but you still see these little channels cut through it. You still see little depressions in it. There's no such thing as a perfect plain. And, and out west, they're a little deeper because they've had longer time to cut down and stuff like that. And the Rockies were lifted up relatively quickly. If net uplift is, that rate is higher than your erosion rate is, obviously you're going to build mountains.
They also have the Pangea racing to get to where the continents are today. And I'm not sure when the shifting of the continents is supposed to occur, if it's supposed to start when the rain starts, or if it's supposed to start at the 150 days when the receding starts. But that would definitely affect how water is receding, wouldn't it?
Oh, yeah, definitely, especially if it's plowing through it 2 meters a second, which I believe is what Austin said it was. Heat problem part 75 right there. We won't even get into that one. But, yeah, and Pangea wasn't the first supercontinent anyway. This is as far back as they can go. You think that would be mentioned in something that holds inherent truth, I mean, the continents shifted about. It's just something, even if it's vague like that, there's no mention of that.
This has absolutely nothing to do with geology, but the other thing that doesn't make any sense at all is how all of these continents could have shifted. All of this water could have come through. It's all of this, massive moving of rock. And yet when it's all over, there's still vegetation there.
Oh, yeah.
Yeah, there's an olive tree standing there that this dove can go get a branch from.
That's a good point. That's a good point. Because the writers of the Bible only understood local flooding.
Right.
To them, it may have been their world, but it wasn't the world.
Right. So if we had this massive shearing of the plains, why are the trees still standing?
Yeah. And why aren't the ones that were ripped down mixed in all this sediment that would have been ripped from the surface? In real science and hard science, and geology is a hard science, if you gotta put something forth that's testable, you can't just put a bunch of diagrams up and talk about something. I say this so often, and I'm so tired of saying it. Arguments, antidotes, and analogies are evidence of two things: Jack and you know what. You can't argue your way into evidence. You can't argue your way to falsify a scientific concept. That's not how that works. Especially one, they're trying to falsify all of everything we know about geology. So you got to start at the basics. You got to start over, and you got to start presenting testable hypotheses so others can test them. They're not even doing that. And papers by Baumgartner and Austin and all them. But you look at them, and when they do put models in their papers, they basically take the model we use and just say it happened really fast. That doesn't answer anything. That's not a solution. You can't take our model and say it happened really fast and then make up a story behind it. That also is not science. Arguments in science are starting points. Analogies are teaching tools. That's why you see them in textbooks. My structural geology textbook has analogies in it. But you don't see them in scientific papers because you're past that stage. You already understand it, supposedly, if you're reading the paper. Papers aren't teaching tools. That's not their purpose.
In more channelized phase, different features are formed, and these features are superimposed on the features already produced during the sheet flow phase. And these would be canyons, valleys. After you've already eroded a lot of material, you form the canyons and valleys during the channelized flow phase. And when you're forming canyons and valleys, and in some valleys, the flow is going so fast you form planation surfaces along the edge called pet.
All right, this makes no sense to me. If the water is receding and you've gone through this alleged sheet phase, and now we're going through a channel phase, if all of this land is flat, how is this receding water creating a channel that would create a canyon?
The only way it would do that is if it went away even faster. What you said makes sense. Mm-hmm. And I'm glad you followed what he said, but I guarantee you the average person probably didn't even follow that. What they're trying to do here is basically say during the main part of the flood, you had all the shear off. Then I guess as it receded, it formed channels and stuff. That's my guess. But, they never really say that. And I think he's probably going to go to the grand staircase.
Where water was going perpendicular to ridges and channelizing, it cut water gaps all the way down to where water's running through the mountains or the plateau or ridge, and you cut wind gaps that aren't cut far enough down. And also, as the material eroded.
Do you know what he means by that?
No, I actually don't. But he formed a V shape with his hands. Mm-hmm. And that's the young stage of a river. Like if it's in the mountains and it's down cutting still. Mm-hmm. Like in the old phase, it doesn't down cut anymore. It cuts laterally. But in the mountains, it's a youthful stage.
During the sheet flow phase, in wide currents, gets deposited along the continental margin. It's just taken clear off the continent. And it forms the thick sediments of the continental margin, of which the profile is called a continental shelf at the top. And then you have a drop off called the continental slope. And off of some continents, you have a gradual descent into the deep sea, and that's called the continental rise. And those sediments, of which sometimes they're 15 kilometers, 20 kilometers thick off the east coast of the US, for instance, 25 kilometers thick in the Gulf of Mexico, just thick sediments from the runoff of the continents form the continental margin sediments that
Is that correct? Is
No.
that how that's formed?
Well, no, it's not how that's formed at all.
Okay.
He gave it correct, like, cross sections, but
Mhm.
his interpretation is completely wrong. We could drill into that. We see the coastal plain sediments actually go up to southern Illinois. Coastal plain, those continue down into the continental shelf. Those are sedimentary. They're continuous. We know this from drilling. It's not different. And how do you deposit that in his model? The oceans just happen to be perfect. Those sediments are continuous from land to the sea. And that happened because as North America split from Africa and Eurasia, that's on a passive margin. You form passive margin sediments. You get these thick sedimentary packages. And this isn't the only place you see them in the geologic record. You see them all the way back to the Precambrian. The Huronian supergroup is a passive margin sequence when the continent, relative to modern South, stopped at Lake Superior. Well, what's Lake Superior now? There was no Lake Superior then. So these are preserved in sedimentary rocks that predate even the Great Unconformity. These are just how passive margins form. You're going to get sediment as those continents drift apart. There's nothing to move that sediment. And if all that stuff was dumped there simultaneously, we talked about this. Where's the tree trunks? Where's the huts? Where's the boulders from in Alaska or something? Where are these things that you would expect if something just drops energy?
This bathtub ring extends way out. Continental shelf can go out hundreds of miles. If you can drain all the ocean water and see the geomorphic features of the surface, this would be
They're clearly using Google Earth, and he went from the eastern side of North America to the western side. And of course, there's no scale because young Earth creationists don't know what that is. And there's no north arrow, but I could tell that was the western edge of the United States and up into Canada. So if you notice there, just from this, assuming it's at the same scale as the eastern side was, that continental shelf doesn't go out very far. Nowhere near as far, because that's an active margin. Subduction is actively occurring there. So the sediments, that plate that's diving under the one that's laying these sediments, is bringing some of those sediments back down into the mantle with it. You don't get a passive margin. You don't get the same geology. And most of that stuff isn't going to be nice layer cake geology of sand like they are on a passive margin or limestone or whatever. So whatever sedimentary rock gets deposited, it's going to be more jumbled. Okay,
so you're telling us that the continental shelf is not uniform around the globe.
Yes.
As you would expect it to be if it was formed by a global flood.
Yes, and there are some places where there's no continental margin, essentially.
Ah, interesting.
Yeah. You basically get land, and then maybe 5 kilometers out, if that, it's the abyss. The Aleutian Islands in Alaska.
We're in the lower canyon of the Clark's Fork River Valley before it enters the Bighorn Basin. This is a great location to talk about tectonics. That's vertical changes in the crust of the earth during the recessional stage of the flood. Now
we know that the tectonics moved during the recessional stage. Now they've got to cram the movement of the continents into an even shorter period of time because it didn't occur in the first 150 days of the flood.
Oh, apparently not. And they've got a deal. It sounds like tectonics is going to be described as a sheerly vertical motion. It seems to be that people don't understand there's a third component here. There's lateral movement. You get stuff. I mean, there are big, huge sheets of, not sheets. There's thrust faults of deposits thrusted miles over other ones. This is when you get older over younger stuff. The Lewis thrust is one of these. It's Glacier National Park. That's why there's Precambrian rocks there and not Mesozoic or Paleozoic rocks, because they've been thrusted over. It's what we call a thin-skinned thrust fault. That just means it wasn't very deep. It was a shallower thrust fault.
You see the edge of the Beartooth Mountains, and actually it's part of the Beartooth Mountains, that dark area there, sloping down with a flat surface. And on top of that are Paleozoic, mostly limestones piled on top of it. Well, as the Beartooth Mountains uplifted and this limestone area uplifted, it bent the rocks on top of it.
There's a fucking bird bent.
Yeah, he's going to go way into the bent rocks here. I know how much you hate the bent rock.
Yeah, I'm not going to say anything.
Angle and eroded. This material that used to be on the Beartooth Mountains way up there got washed off, and it moved east and piled up into a huge, what I call flood fan of limestone blocks and rocks cemented together. This fan probably had an angle like that to the Beartooth, and as the Beartooth continued to uplift, it became an angle like this, about 30 degrees dipping down towards the east. And then this area was eroded somehow, leaving erosional remnants of that flood fan out to the east about 2 miles.
Okay, this thing that he's calling a flood fan, do you know what that is?
Yeah, he's actually kind of describing alluvial fans. If you could see the Beartooth again, you'll see what an alluvial fan looks like. That's fine. This is fine. You see the mounds, you get the level flat stuff, and then you get in the background, you get the mountains in between there, you get this moderately sloped stuff. Mm-hmm. Those are alluvial fans. They were glaciated. How do alluvial fans form? They form when you have a high topography, like a mountain like this, and rivers and channels can't really develop effectively for whatever reason. And since this was glaciated, this plain is probably some sort of glacial artifact. It's not water at all. And if that glacier, we'll just say, did its thing, and all of a sudden you've got this cliff right in front of the Beartooth, well, the streams aren't going to be able to downcut that fast enough to step. Now, I do see a stream over here, so this might just be a floodplain for all I know. Because like I said, after they establish a baseline, they start cutting laterally. They stop cutting vertically. So I'm not an expert on the Beartooth, but these alluvial fans are when material gets eroded quickly and energy gets lost really fast. This is what you get. You don't get continental margin deposits. You don't get pyres. When you go from an area of high energy to low energy, you get these fans. These fans will be conglomeratic sandstones and stuff like that. It's coarse grained stuff. There's no shales in that. There's no native limestones. I mean, you might have blocks from the limestone mountain, in there, but you can't, there's no lakes here. There's no rivers here. It's just terrestrial deposits.
During the recessional stage of the flood and the Beartooth Mountains uplifted, there was a fault here called the Beartooth Fault, where the Beartooth Mountains rose, the granite in the Bighorn Basin sank. You find the granite 10,000 feet below sea level. Well, up on the Beartooth, it's 13,000 feet above sea level, indicating a change of 23,000 feet at the Beartooth Fault. You can see in the background these strongly tilted rocks. In the Bighorn Mountains to the east, we have a similar uplift and tilted rock. You generally don't bend rock unless it's really deep and under pressure and heat without breaking it. So this bending to vertical strata, tilted from about 30 degrees to vertical here, probably implies that the sediments were not quite solidified, or they were partially soft.
Young Earth creationists love to talk about how you can't bend solid rock. Yes, you can deform solid rock. This is structural geology, goes into depth upon this stuff. It has to do with, compressive strength and stuff like that. Strain versus stress, elastic, plastic, brittle failure, all this stuff. If stuff is confined with other units on top of it, it can deform. It just stays in that plastic stage much longer, and time does do that. I could take a piece of paper, and it just gave me an idea. I could take a piece of paper and a rock, put it on my bed, put the rock on, take it off. You're going to see a little dent in it, right? I have plastically deformed that paper. Every solid plastically deforms. Now, if I put that rock back and let it stay a day or two a week, then pull it up, I'm going to have an even bigger depression. That's not going to pop back into shape. Now, that paper's solid. So time does matter.
It also implies another thing. If this uplift was slow over millions of years, these vertical features would all erode in that time, and you wouldn't have features like this. And same with in the Bighorn Mountains, where you actually have overturned strata.
Were those actually formed over millions of years, or was this formed in a faster uplift of plate tectonics or from glacial deposits?
Yeah, it's not as simple as young Earth creationists like to portray it. And that Beartooth Mountain itself is obviously older rock. And yes, you get thrust faults as the mountain building range. You can get overturned rocks. That's not unusual when this happens because we have a lateral component as well as a vertical to this faulting and stuff. Now, that stuff was deposited, I don't know, millions of years ago. You can see the bedding in it. Okay. So that would have been deposited initially level and flat. My guess is probably during the Cretaceous and the Jurassic seas that filled the area at the time. That's my guess. The seas retreated, and then that area started to get uplifted. You started to deform the rock, and you get overturned things. But as this is happening, as you're building this, as long as your uplift rate is quicker than your erosion rate, you're going to get mountains.
Ah, okay.
So it's not a matter of, I mean, modern erosion, I mean, it's probably millimeters a year in this area. And on the bottom, I'm sure it's a lot slower than it is up top of the Beartooth. It has to do with precipitation, elevation a little bit, not so much. It has to do with the angle of the slope that's being eroded, all that stuff. And then you have, millions of years after that, the glaciers come in. It's alpine glaciers. But you look at the valley that's right by Beartooth Mountain.
Where is Beartooth Mountain?
It's in Wyoming. Of course, he doesn't give you a map so you can actually see the topography and give it for yourself, So, but Beartooth Mountain, just south of that is a valley. Now, this would have been, during the Ice Age, would have been host to alpine glaciers. It's south of the maximum continental glaciers, but it still would have had alpine glaciers. And the valley to the southwest of it is a combination of faults, the geology, and a glacier moving through there, because now it's occupied by a river. So, and you kind of see that river in the background. So you've got all these things that have to happen before you can have what you see. That rock that makes up Beartooth Mountain had to be deposited before you see that modern landscape. You can't form a landscape out of rocks that don't exist. And he's not even talking about those rocks.
You wouldn't have that if this was slow uplift over millions of years, because it would erode. Erosion's pretty fast on a million-year time scale. This implies rapid uplift, consistent with what we expect during the recessional stage of the flood, when the mountains rose and the valleys sank down. And this theme of the mountains rising, the valleys sank down, is a theme all over the earth, even on the ocean bottoms. Most of the ocean bottom consists of abyssal hills, which are faulted up hills.
Well, in one respect, he's right. We do have oceans and valleys everywhere. And he's right that, we get up, when the uplift is greater than the erosion, we get up mountains.
Yeah.
The only thing is that it didn't all happen at once.
Yes, and not to mention, he's clearly got a vertical concept only of plate tectonics. At least of the fault. He may not even realize that faults are a result of plate tectonics. Everything comes down to tectonics ultimately. And here's the thing with the ocean basin is it's generally mafic rock, and the continents are generally felsic. What's that mean? Mafic rocks, for all intents and purposes, we'll say basalt, because as the plates move at your spreading centers, you get those type of chemical concoctions that will form basalts, and stuff like that. But the continents aren't as heavy or as dense, I should say. They're more buoyant, and they don't get subducted. And you just look at a geologic map of the Earth, and you can tell the oceans are entirely different in their geology than the continents are. And that's because the oldest ocean crust on Earth is in an eastern part of the Mediterranean. I'm not going to get into that because we're not sure the age. It's somewhere between 300 and 400 million years. It's like a remnant of a very old sea. Other than that, you're looking at 200 million. Yet we got rocks on the surface of the planet that are at least 3.8 billion years old up on the continents. That's because the continents don't get subducted. It has to do with tectonics, the mineralogy, you know, the rocks, all that stuff that I'm sure he's not going to talk about.
We discussed the sheet flow phase. We have to talk about what causes the water to drain off the continents and about the erosion of the continent. Psalm 104:8 tells us that the mountains rose and the valleys sank down when the...
And he's referencing the Bible. He's already introduced miracles into the part of this, which is completely unscientific. That you can't use the Bible because there's no references. There's no who wrote it. There's different versions, even in English, that say entirely different things. We don't know who wrote it. There's no citations. There's nothing like that in it. So scientifically, I mean, they used it back in the day because they had to. They had nothing else to go on. They were starting out. But now the scientific method is pretty much standardized. I can't use the Bible as a reference any more than I can use, like, you know, a comic book or something like that. But at least I know who wrote the comic book. I don't know who wrote that verse. I don't know when it was written. I don't have any of that information. I would need to go back and not fact check, but to see if your hypothesis has any weight. I can't replicate what you're, you know, the things I need to do in order to see if you're correct or not. That's not sitting there discarding the Bible. That's sitting there bringing up deliberate, intentional things that are inherently wrong with using the Bible in the way he's using it. And it's not, you know, even if God did send it down and write it, I still can't use it because there's no citations or anything in it.
I wasn't complaining about that particular passage only because it is so generic. It really doesn't tell us anything. It just says the mountains rose and the valleys sank. Well, yeah, that did happen.
Yeah, it's very vague. And you know, creationists are always quoting because you can pull out whatever you want from that. And you're right. Mountains have gone up, valleys have gone down, but that provides no mechanism. What is that based off of? Nothing. None of this is given in that verse.
The form of guyotes, which are formed near sea level. These are guyotes are flat-top seamounts, and a seamount is a volcano, an underwater volcano. They're planed at sea level, near sea level, and now they're 5,000 feet below sea level, indicating that the ocean basins have sunk and the margin along the continent has sunk. We have evidence of...
He did show the Aleutian Islands there. And it's not like 5 miles, it's more like 50 before it drops off, what I said before. But yeah, he's talking about seamounts and stuff like that, those geomorphic features. They're not as flat as he thinks they are. And you do have ocean currents as well. And depending on how they formed and why they're there, they don't all form the same way. But if you look at even a shield volcano or a typical textbook cone volcano, they tend to be relatively flat on top. They're not as steep-sided. Now, that's not always true. I get that.
You know, he was talking about underwater volcanoes. Is it true that they would have had to have been on the surface at one time, or didn't volcanoes form underwater?
They never had to be at the surface.
Okay.
Volcanoes can form underwater. Hawaii, the Hawaiian Islands at one point were just underwater. You know, it's just you happen to have enough melt rise up to break the sea level. That's it.
Between the top of the Appalachians and some of the big cracks that are filled with sedimentary rocks in the coastal plain and on the continental shelf off the East Coast. So you had a lot of upward vertical tectonics, and this is what drains the floodwaters off. As it's draining, it's going to erode the land during the retreating stage.
He's talking about the Appalachian Mountains being uplifted, and the Appalachian Mountains are very complex. They've had several what we call mountain building events. We call them orogenies. There was Precambrian land added to it, Phanerozoic land masses added to it. It's no longer active because it's near that passive margin. In order for the Appalachians to still be active, you need subduction in that area, and there's no subduction currently going on. So all the faults that are there, all the deformation, the anticlines, the synclines, those all predate. They go back very far. I think the last orogeny there was probably during the Ordovician. So, you know, you're talking a long, long time ago. They're no longer active. You know, we can measure uplift. This isn't something we can't measure, you know.
When we look at the continents, we can tell that it's been greatly eroded in bulk. For instance, the Colorado Plateau it was estimated that we've had anywhere from 8,000 to 15,000 feet of erosion over the whole Colorado Plateau. Other erosional numbers are in the literature. For instance, in southern England.
Is that correct about the levels of erosion?
In certain parts, probably, okay. But it depends on what he's using for his base. Is he using the top of the Grand Canyon, or is he using the top of the Grand Staircase? And these two things were not eroded at the same time. The Colorado Plateau wasn't always being uplifted. It is now, but that wasn't always the case. So, yeah, it's just no frame of reference, no measurements, just talkity talk.
It's been estimated a mile or so of erosion in the Canadian Rockies and the foothills, about another mile. Over the Flinders Range of Australia, it's been estimated about 20,000 feet. In the Appalachians, it's been estimated about 20,000 feet of erosion. Now, I ran a calculation to verify some of this erosion, and there's two ways you estimate the erosion. There's lots of coal in the rocks. Coal needs sediments above it, and it needs heat and pressure. So from the coal rank, which is determines how hot it was, you can figure out roughly how much overburden. And based on coal rank, you can estimate about 20,000 feet of erosion in the Appalachian area.
That is a thing, what he's talking about, the grade of coal, and we can estimate how many sediments were maybe on top of that. But that only works in places like Illinois, where there hasn't been much change. The Illinois basin, there wasn't much deformation. Essentially, it's flat. Even the Paleozoic stuff is flat. But you can't really do that in the area of the Appalachians, because you can get higher grades of coal just through compression, just through tectonics. And I'm assuming that stuff is Carboniferous in age, just like it is. Most coal comes from the Carboniferous. It doesn't come from the Cretaceous. It comes from the Carboniferous. I mean, there's other ways to get higher grades of coal, is the point of that, other than just dumping a bunch of dirt on top.
Another calculation is to check the sediments off the East Coast, where the floodwaters were eroding the mountains, taking those sediments to the east and deposited them in the continental shelf slope and rise. From that estimate, and by the way, we have those estimates based on seismic reflection profiles. We can find the igneous metamorphic basement and the sedimentary rocks have been estimated. And again, it comes out close to 20,000 feet of erosion for the Appalachians.
He was talking about the continental shelf and going to using seismology and looking down. That's true. But then he said erosion of the Appalachians. That's on the surface. I think I'm just going to take that as a misspeak because he's a meteorologist, but that didn't make any sense. Okay. And he did mention, over the igneous and metamorphic rocks. Yeah, but how do you get metamorphic rocks? You got to metamorphose something that already exists. And what can become metamorphic rocks? Igneous, sedimentary, or other metamorphic rocks. You can't, how did those get in place? He's just glossing over all that. He's just using landforms because he can say anything he wants really about that. He's not showing you any of the geology.
There's a calculation that you can do based on north of the Grand Canyon. There's the Grand Staircase where the sedimentary rock
I knew that was coming.
Down to the north about 3 degrees. And there's a series of cliffs and steps, cliffs and steps. In other words, there's 5 of them of sedimentary rocks and a 6th at the very top that's volcanic. Based on that, if you extrapolate those sediments up over Grand Canyon area, you can show that around 10,000 feet of sedimentary rocks were taken off as a sheet, forming a planation surface over that whole area. That would occur.
Sick of talking about this. Well, here we have arrived at their 2 favorite places in the universe where they take local geology and extrapolate it globally, which is something you should never, ever, ever do. What he's actually talking about is a valid geologic concept. Maybe he'll show a cross-section. Maybe he wrote, it's called the law of lateral continuity. But you've got to be, that's supposed to be used on shorter distances, but you can use it on further distances as long as you have the same rock on both sides. But you can only know that by looking at the rock. Now, the Colorado Plateau wasn't sheared off because, you know, you have all this Paleozoic stuff under it. You have all this, you know, other older rocks, sedimentary rocks under that. So those had to be deposited before you could shear anything else off. And, you know, other young Earth creationists put those rocks above the flood or at the end of the flood or during the flood, you know, and he's talking about it as if they were already there. You can estimate the deposit thickness that way, but that's all you can do. You can't extrapolate that indefinitely. You can't say that it was there and that it was gone, thus for flood. You know, because like I said, the Colorado Plateau is something very complex. There's even something there called the Paradox Basin, which does kind of baffle geologists. We think we have it figured out now, but this is such a complex area, and there's different things going on that one catastrophe can't explain any of it, let alone all of it. And that's why he's showing you a zoomed out picture and not talking about the actual rocks themselves.
During the sheet flow phase of the retreating stage of the flood. Another calculation on the Colorado Plateau I made near the Book and Roan Cliffs near Price, Utah. Again, the sediments, they tilt about 6 to 8 degrees to the north. And based on trigonometry.
This is what we do sometimes. This is, you're trying to use the law of lateral continuity, but notice it stops and there's question marks. There's a reason why those lines stop there and don't keep continuing. Probably because there's some sort of geologic structure there that messes with this. So with any confidence, you can only go maybe this far. You can't just keep extrapolating it, but this is representing the law of lateral continuity. You're just not continuing it to anything on the other side. We do this to kind of reconstruct anticlines sometimes and synclines and domes. It is useful for that. But other past that, there's really nothing you can use this for. And this also says nothing about erosion rates. It has nothing to do with that.
Stephen and I were only 20 minutes through the video at this point. You've seen over an hour of us. Stephen will be back next week for part 2. One thing I learned in making this is a reaction to every part of this video is tedious and hard to make interesting for you, the audience. So in next week's edition, I'll use only the parts of the video that address alleged geologic problems for an old Earth. Thank you for hanging with us to the end of this one, and live your life.